Hello, this is the key to the constant velocity particle model, content checkpoint number 2. So the first thing here I want to talk about is just up at the top. It says make sure you go back and check out content checkpoint number 1 because there's a lot of information on there. It's still going to be something that's important that you know all of those things for this test, so try that out. In addition, we're going to add some new things here, so we'll do some problems where you compare two objects together. That's in section C, I believe, of this. You're going to have to do a lot of things with velocity versus time graphs that we hadn't done on that first content checkpoint. All right, and then we'll do this thing with displacement, where we talk a little bit about displacement and velocity versus time graphs. And then, generally speaking, we'll talk about in class a little bit more, but how to know from a graph whether, or how to know from a motion map that an object is traveling with constant velocity, and we'll talk about that a little bit as well. So going down here, we have another one of these problems where I have a person and they're traveling in a path, and in this path we're going to use some of these vocab words that we've been using throughout. And so the story problem here is that a bank robber running away from the police. This is the robber starts at point A, runs due west. He arrives at point B 1 hour later. At that point, the robber gets in a boat, sets off downstream in a river, traveling due south for 2 hours until he's caught by police at point C. Point C is approximately 41 miles from point A in the direction 79 degrees south of west. And so in this one, I'm just setting it up. I've told you that C is in the direction 79 degrees south of west from point A, and we'll use that direction later on. And so I'll never have you try and derive one of these complicated directions where you have like something that's south of west or south of east or north of west or north of east or anything like that. You'll never have to think that part through. I'll just give you the direction directly in the problem. So keep that in mind. So this first one here is describe the position of B in relation to point A. So we're looking at B and we look at point A. And if somebody asked you where B was located relative to point A, hopefully you would recognize that you need a distance and a direction here. So B is 8 miles away, so it's 8 miles, and then you have to say the direction, so it's west of A. Okay, hopefully that makes sense, just knowing your cardinal directions on a map there. The displacement for the entire trip A to B to C. Well, for displacement, it's a vector. We only look at the starting position and the final position, and then we say, you know, how it's changed from beginning to end. So for displacement, we're really only looking at A and C and how it's changed going from A to C. And so for the displacement, we know that it's 41 miles away. And the direction there, going from A to C, I've given you in the problem up above. It's at 79 degrees south of west. For the total distance traveled is a scalar. It means there's no direction associated with distance traveled, so you just look at the path and count up the total amount of distance traveled. So distance traveled here, you add up the two legs of this path. Distance traveled. Okay. And you should see that it goes 8 miles and then it goes 40 miles. And so if that's the case, we do 8 plus 40, which equals just 48 miles. Alrighty. So that's how that one goes. No direction associated with distance traveled. Number 3, it says, what's the speed of the robber, B to C? So we look B to C. To find the speed, you take just the distance over the time. So the distance is 40 miles, and it took 2 hours to get there. All right, so 40 miles. Speed equals distance over time, which equals 40 miles over 2 hours, which equals 20 miles per hour, and that's the speed. All right. The velocity equals the change in position or the displacement over time. Just looking B to C, the change in position is 40 miles south. It goes 40 miles south. So again, we say 40 over 2, all right, which equals 20 miles per hour. But since this is a velocity, we need a direction here. Going from B to C, it's going south. And then finally, 4 talks about the average speed and the average velocity when we're going A to B to C. To do the average speed, we say that that equals the total distance traveled over time, again, for the whole trip, which in this case, we went 8. We calculated this up above, but we went 8 and we went 40, so 48 is the total distance traveled. The total time there is 3 hours, all right? So 48 divided by 3 gives us 16 miles per hour. For the average velocity, that's equal to the displacement over time. All right, we're just looking A to C now, so that's the 41 miles over the time, which is 3 hours still. All right, and if you calculate that, you should get 13.7 miles per hour. But again, since this is a velocity, we need a direction in here. And if you're going A to C, then you're going at 79 degrees south of west. Okay, so hopefully after we've been through enough examples of these, those are sort of starting to make some sense to you, but if they're not, make sure that you come in and ask me about those. Moving on to the next section here. In this section, I give you a velocity versus time graph, and I ask you to create some other representations of the motion. And so what I wanted you to see with these is that we can figure out the displacement by looking at these velocity versus time graphs. You find out the displacement by finding the area. And so the area here on this first one is 3 meters there. The area up above here, we get 4 meters. It's going 2 meters per second for 2 seconds. The first one was going -1 meter per second for 3 seconds. And so that gives us the distance traveled. If you want, you can think about it as displacement and throw a negative sign in there because on that first one because it's -1 meters per second. All right, I think that makes sense. All right, so it goes down 3 and then it goes up 4. Our initial position was -4. All right, so if we're going ahead and doing this, what I would do is I'd mark off here my initial position. I call that -4. All right, I know that after 3 seconds, I've gone down 3 because my velocity is -1, or you can just think about the area of the velocity versus time graph that we just found. So in the first 3 seconds, it goes down 3. So I'm going to try and make some pretty wide seconds here because I have so much space on this axis. Okay, so after 3 seconds, I've gone down 3. So I'm, say, down here, which would be at -7. All right. Then, in the next 2 seconds, I jump up by 4. I go up by 4. And so I end up, in the next 2 seconds, I'm up 4 from this, which would be at -1. So I'll plot that. It should be a little bit above the first point, and it should happen over the period of 2 seconds. Alrighty. So that's that, and I'll just mark that this is at -3. Alright, and so what we've got here is it starts at -4, it drops down to -7, and then it bounces back up here to -3. The motion map is a little bit easier to do even. So we start with the initial position that's given. It says it's -4, so you have to mark a 0 somewhere. It doesn't really matter. Since all of this happens to the negative part, I'm going to put 0 over here, and actually I'll write that up above, just so the 0's out of the way. All right, and so we start off at -4. So I'll start off here. All right, our original velocity is -1 meter per second for 3 seconds. So I go -1, -1, -1. All right. And then this is one of those cases where I'm abruptly changing directions, you see here. So actually, I'm going to drop down one level just because I'm going to change directions immediately and then go +2 and then +2. All right, so we've got this, and then another arrow, but this arrow does not have a dot on it. And I'm going to try and just like really darken in my dots here so that they're visible. A dot here, and then a dot up here. I'll put in the congruency marks. All right, and that looks good. Okay, for the written description, it's pretty long, but you start with the initial position. The initial position is -4, and then we say that it travels with a velocity of -1 meter per second for 3 seconds, and then it abruptly changes direction and travels with a velocity of +2 meters per second for 2 seconds. You can get all of that directly off the velocity versus time graph. I'm going to go ahead and put it on screen here. If you want to pause the video and read that and think about it for a minute, maybe that would be a good idea. All right, moving on to the next one. This one, similar. You can just look at the areas and see what the displacement would be for these different areas. In this first part, it goes 6 meters. All right, and then in the second part, it goes 2 meters. It says assume an initial position of 1. All right, so for the motion map, we're going to have 1. We're going to start at 1, and then we're going to go up to 7, and then we're going to go up to 9. All right, so leave plenty of room on the positive side of this. We'll start off here right at what we'll call 1. All right, and then I know that for the first, after 3 seconds, we got 1, 2, 3 seconds. After 3 seconds, it should be all the way up at 7. So I'll make a mark up here at what I'll call 7, and it should be up there. And then we'll go an additional 2 seconds, 1, 2 seconds, and it should be up to 9. I'm going to try and draw those numbers a little bit bigger. It's hard here with the smart board. So 9 and 7. Alrighty. And so up here, we'll put another mark there at 9. All right, and so we see here that it goes up quickly at first, and then it kind of levels off a little bit. All right, and that's what the motion map, that's what the position versus time graph looks like. For the motion map, on this one, since everything's positive, I'm going to put the 0 here, and this we'll call this 1. All right, so initial position is 1. It's traveling with a velocity of 2 meters per second for the first few seconds here. So 1, 2, all right, that's 2 seconds, and then 3 seconds. Just darkening those dots so that you can really see them. And then it's going to be only going 1 meter per second after that. Give these a single tick mark here. Give these double tick marks. All right, and that is that. So it's going fast at first, and then it goes a little bit slower, but it stays going in the positive direction. Writing down the description of motion for this one, again, I'll just say it out loud, and then I'll put it on screen, and you can copy it down. So the initial position is 1 meter. That was given to us. And then it travels with a velocity of 2 meters per second for 3 seconds. And then it continues on, and it travels with a velocity of 1 meter per second for an additional 2 seconds. All right, and that is that for those. In this next section, what we're going to be doing is comparing the motion for two different objects. So the first thing that we have you do is describe in words some differences here. The things that you'll be comparing usually are the velocities that they travel with, or the directions, or the steepness of the slope, or the speed, and things like that. And so I've got a list of things that I think are just relevant things to compare with, and then we'll go through and we'll make the other graphs here, and then we'll move on. So the first thing I'll do is I'll just enter in what I think is a good description of the similarities or differences, and in this case, mostly differences here between these two graphs. So you can see here I say object A is at rest because its position is constant there, whereas object B is traveling with a positive velocity. Also, another relevant thing to compare is that object A's position, its initial position is positive. Object B starts at the origin, or starts at 0. So going with that, what we're going to do is plot out their velocity versus time. So we look at the slope, right? For object A, the slope is 0 because it's a horizontal line. So for object A, actually, I'll just say A here because I think that'll be less writing. Whereas B is going to have a positive constant slope, so a constant positive velocity here. So B goes up above. For the motion map, A is going to be, I'll put 0 here so we have this as a reference. For A, it's going to be staying in the same place over and over again. So for A, we just have a bunch of dots that are sort of all together in the same place. For B, it's going to be starting at 0, and it's going to be heading in the direction. Actually, I think I'll go a little bit further along so that what we have here is that the last second, it should line up here. I didn't quite get that right. Because what happens is, well, and it doesn't have to be, I guess it doesn't have to be 4 dots. I just did 4 dots for A, so I wanted to do 4 dots for B as well. That way we have 3 seconds for each of them. So these are all the same for B, and then it ends up in the same place as A is, and so it should be even there for B because it ends up at the same. B's final position is where A is, I guess, is what I'm saying here. So another relevant sort of point there to pick out. For number 2, as I said, I'll go ahead and put my description in there. So you can read that there if you want. We've got object B is traveling in the positive direction. You know that because its velocity is positive, whereas object A is traveling in the negative direction. You know that because its velocity is negative. The other thing here is I said that the speed of object A looks slightly larger than the speed of B. What I'm saying there is A, if you look at how far it is away from the t-axis, it looks like it's a little bit further away than what B is. So it's going to be going slightly faster than what B will be going. For the position versus time graph, I'll have A going here pretty quick. All right, oops. And then for B, as I said, since it's going to be going slightly slower than A and in the opposite direction, I'll have it here where it's going for about the same amount of time, but it doesn't quite cover the same distance that A does because it will be going slightly slower. We don't know necessarily where they'd cross. I have them crossing here at 0, but you don't know for sure that they would cross there. This is just one possible thing where this works out. I didn't say what the values were in any case, so you can't know. It's kind of impossible to know. For the motion map, because they're going positive and negative here on the position, I'm going to put 0 right in the middle. I'm going to say A starts off here. I'll just do something like 5 dots. All right, so A traveling in the negative direction. Oh yeah, I switched those around here in this. I'll fix that in just a second on the position versus time graph. Because I said object A has a positive initial position, so this one is actually B, and so I'll redo this really quick here. What we want here is actually to have A starting positive, and it has a sharp negative velocity, whereas B starts out negative and has a slightly less slanty positive velocity. So it looks pretty good there. Alrighty, so B, in this case, this one was A. We've got A here, and this is B. For B, the way this motion map shakes out is it's going to be going the opposite way. It starts off a little bit negative. But it's going to be going with smaller arrows in the positive direction. Actually, and that's one too many arrows there if I want to go for the same amount of time. 5 dots for each, so we'll stop it right there, and that is B. Okay, moving on to question number 3 here. I'll go ahead and take a second and write out that written description of the differences. Alright, so you can read that. It says object A is traveling in the positive direction, whereas object B is traveling in the negative direction. Object A had a negative initial position, whereas object B has a positive initial position. They're traveling the same speed and have the same final position. So these are all things that we can read from that motion map. For the position versus time graph, to kind of make this work, you can see they have the same final position, and that the final position that they both have is positive. And so we know they're going to end up here sort of at the same point. Oops. So what I'll do here is I'll sort of put that out. And then since they're the same speed, they should have the same slope, just one positive and one negative. All right, so it should look something like that. All right, for the velocity versus time graph, and I should actually indicate here that object A is the one that's going in the positive direction here, so there's object A, and object B here is on the top. So over here, object A has the positive velocity, and object B has the negative velocity. So that is that. I won't exactly have you do the same thing, but I want you to be able to compare some graphs, because I'll have you do some comparison between different graphs when it comes time for the exam. So you should be able to see some of these sorts of things. I'll give it to you in a multiple choice sort of setting on this one, so hopefully it shouldn't be too bad, and you can kind of pick out the comparisons that make sense. Here to the last page, this is not something that we spent a whole lot of time on in class, but it's also something that isn't very difficult, so I'm going to try and remind you about how this works, and then hopefully it shouldn't be so bad. So for one of these, what we do is we start off with the equation for a line, y equals mx plus b. All right, so this whole context is put in that, but for the context of a position versus time graph, you can rewrite that as the position equals the velocity times the time plus the initial position, all right? And so it's the same thing. It's just now we've put it in physics terms. The y variable is position, the slope is the velocity, the b, the y-intercept or vertical intercept, is the initial position, all right? And so then what we can do is we can pull off here these different values. And so you can see, for instance, the slope, which is equal to the velocity, right, in this case, is going to be, it goes down 3 and it goes over 4 on the graph that we've got. So we'd say negative 3 over 4. All right, and then the initial position if you look there, it's equal to 3 because at time 0, the initial position or the vertical intercept is 3. And then you just plug it into this equation. So x equals negative 3/4 times the time plus the initial position, so plus 3. The velocity here we calculated was just negative 3/4. All right, and for this model, velocity is constant, so that's all you'll get for that. For the second one, things are a little bit different. It says the initial position is 5 meters, so actually what it tells us is x original is equal to 5 meters. What we can read from the graph, because it's a velocity versus time graph, is that the velocity equals negative 2. All right, and so then if we're plugging it into this, we know that x equals negative 2, because it's the velocity times time here, plus the original position, so plus 5. And then in terms of what the velocity is there, it's just negative 2. All right, so coming up with equations for those things isn't too bad. I just wanted to touch base on that here really quick before we ended off this unit. All right, I know that was a lot, and there's a lot of things in this packet and in the first content checkpoint, so if you have any questions on anything, make sure that you come in and see me.